Hello, and welcome to a Print-to-Perform video enablement manual. In this manual, I will teach you how to set up and run a powder bed fusion simulation. I will be using the 3D Experience platform to explore the process setup, simulating the build process and evaluating the results. I will also make sure to address handling details during the training, so you don't need to worry about catching up at all. You can review the material over and over again until you feel comfortable moving forward. That's it for introductions. So let's get started. Let's take a look at how to generate scan path information using the powder bed fabrication app. So the first step is to import a geometry onto the platform. To do this, you just go to the Add menu onto the top bar and click Import. Then click on the browser icon and select the bridge_model.3d XML file. Then click OK. Next, let's open the imported file from the Action toolbar. So here, if I go to the specification tree, you can see that the material has been imported into the part. Now, double-click on this material. So this is the dialog box for the material definition. It contains your mechanical and thermal properties, such as density, elasticity, conductivity, latent heat and so on. Next, let's cancel this window, as we no longer need it. Let us now switch to the powder bed fabrication app, and generate scan path information for the bridge geometry. Therefore, go to the V+R quadrant of the compass, and activate the Additive Manufacturing Programmer role. And, click on the powder bed fabrication app. This is the user interface of the powder bed fabrication app. Now, we are going to create a new generic machine and a build tray. For this, go to the Action toolbar, and from the Setup section, select Build Setup. This is the dialog box for the build setup. In the work area, select the part. The build setup dialog box is now updated with the section. In the number to produce box, we can specify the number of parts to produce. I set this to 1. In the next step, we are going to define resources, such as machine and accessories. To do so, expand the machine section, and click on Create a new generic machine. Here, I am taking all the machine parameter as default, except for the recoding direction. Basically, I am restricting the recoder motion in the Y direction, by setting the Y direction to 0. Thereafter, if I scroll down, these are the minimum and maximum recoding speeds. Again, I am taking them as default. Then, click on this green check mark. After that, under the Accessories section, click on Create a generic build tray. Here, you can find the dimensions of the build tray. Let's specify the length and width as 280 mm, and set the height to 50 mm. Now, click OK and close the Build Setup panel. Next, we will position the part on build tray, using the Build Layout command. To do this, click on Build Layout. And here, under the Part to Position section, I will click on the Add Part Instance icon. Now, click on the green checkmark, in order to validate the process. At this stage, click on the OK tab to close the dialog box. Our next step is to create a slicing and scan path. For that, I will go to the Programming section and select Scan Path Generation. In the Slicing and Scan Path dialog box, click on the Create or Edit Rule icon, in order to create a build process. Here, I will take a default rule name. And then, specify the value of the recoding break time to 9 seconds. Next, click on the green check mark to complete the process. Now, we will create a scanning strategy. For this action, click on this arrow. Then click on the Create or Edit Rule icon. And here, rename the rule to Bridge 90. Then specify the slicing distance, which I am setting to 0.1 mm. Now, expand the Scan Path Definition Sequence node. Here, we can define hatching and contouring strategies. Next, click on Add to Sequence. And after that, click on Scan Path Definition. Here, we can rename the core definition as hatching. Also, click on this icon to select the strategy. In this case I am selecting hatching. I will now scroll down under the Strategy tab to define slicing parameters. Here, specify the angle of rotation between the slices to 45 degrees. And set the radial step to 0.1 mm. Then, switch to the Scanning tab. Here, you can find 3 parameters: beam focus diameter, beam power, and scan speed. Set the beam focus diameter to 0.2 mm, beam power to 195 watts, and the scan speed to 1 meter per second. Next, I will scroll up this window and click on Add to Sequence. Now, set the subsequent sequence to contouring. At this stage, rename the core definition to contouring. And from this icon, select the contouring as the strategy. Then, go to the Strategy tab and enter the number of contouring passes as 2. After that, let's switch to the Scanning tab. Here, I have assigned the same values to the parameters as to that of the hatching strategy. Therefore, click on green check mark. Here, we have created the 2 scanning strategies for the Bridge 90 rule. The next step is now to assign the Bridge 90 rule to the part. After that, click on the Generate tab to compute the slicing. We have now successfully generated the scan path. Now, I will click on the Display tab to visualize the scanning strategy, and click on the first slider to visualize the results. If I scroll up, then we can visualize each hatching and contouring layers. We have now created the scan path. To close, click on the green check mark to complete this process. Our next action is to perform a manufacturing simulation, using the Additive Manufacturing Scenario app. To do so, go to the V+R quadrant of the compass. And here, activate the Additive Manufacturing Researcher role. Then, click on the Additive Manufacturing Scenario app. First, select Thermomechanical as the solution type. This is the user interface of the app. It consists of an assistant panel on the right-hand side of the screen. So now, let's start the process by creating a finite element model from the assistant panel. Under the Command section, select Finite Element Model. We can now see that the Finite Element dialog box has been popped up. In the box, rename the finite element model to Bridge 90. Next, change the mesh size of the build tray to 4 mm. Then click OK to close the dialog box. After that, I am going to open up the specification tree. In here, you will find 2 meshes. The first one is a tetrahedral mesh, used for the parts. And the second one is a swept mesh, which has been created for the build tray. However, I will now delete the tetrahedral mesh, so that we can assign a swept mesh to the part instead. To do so, right-click on the mesh, and delete it. Then, select Meshes, and click on Sweep 3D Mesh from the Action toolbar. In the dialog box, select the bridge geometry as the support. Next, set the mesh size to 0.5 mm, and the number of layers to 20. After this, I will edit the meshing parameters of the build tray. So double-click on Sweep 3D Mesh.1 and change the number of layers to 10. Next, if we want to visualize the Assign Meshes, right-click on the Nodes and Elements tab. Then click on the Hide/Show tab. This is how you can visualize the respective meshes. Now, hide the meshes again. Next, let's open up the Properties section. In here, you don't need to worry about assigning solid sections to the part and build tray. This is because the creation of a solid section property is, for the most part, automated in the Additive Manufacturing Scenario app. However, if we look at the Part and Support Properties tab, it is showing an incomplete status. This is because we have not yet assigned a material for the build tray. Therefore, let's remedy this. To do so, click on this arrow next to the Material Palette section, then click on Pick Material. And after that, open up the specification tree. Select the required material. And finally, assign it to the respective solid section of the build tray. After that step, we need to create a connection between the part and build tray. Therefore, I will click on the Connection section from the Action toolbar and select Tie Detection. In the Tie Detection dialog box, specify the position tolerance as 0.5 mm and toggle on Tie Rotational Degrees of Freedom. After that, click on Find Ties. We can now see that the respective tie pair has been generated. Right-click on it, and choose Edit. Now toggle on the Specify Position Tolerance, and enter a value of 0.5 mm. Next, we will create an initial temperature for both the thermal and structural cases. From the Assistant panel, click on Initial Temperatures and select Initial Temperatures from the Command section. The next step is to click on the Part Body selection from the Contextual toolbar. And then, select both the part as well as the build tray as supports. Now enter a temperature value of 299.15 degrees Kelvin. After that, from the bottom left corner of the window, change the analysis type to Structural Analysis. Next, we will assign an initial temperature for the bridge geometry and specify the temperature to 1200 degrees Kelvin. Similarly, I will create an initial temperature condition for the build tray and specify the temperature to 299.15 degrees Kelvin. After this is done, we switch back to the thermal analysis case. Our next step is to define a moving heat source. From the Assistant panel, select Moving Heat Flux. In the dialog box, select the energy distribution type as Concentrated, and then specify the absorption coefficient. Enter an absorption value of 0.45. Also, note that the laser path is computed by the Powder Bed Fabrication app. Leave all parameter as default, and click OK. Now, we will define material input from the Assistant panel. Here, in the Material Input dialog box, toggle on the Follow Deformation option. Then, specify the expansion time constant as 300 seconds. Note that it should be 2 times the initial time increment. Note again, that the roller path is provided by the Powder Bed Fabrication app. Finally, select the roller as deposition procedure. And select full activation type. And click OK. The next step is to define cooling. For that I will click on Free Surface Heat Transfer. In the Free Surface Heat Transfer dialog box, select both the part as well as the build tray as supports. Set the reference temperature to 299.15 degrees Kelvin. And the convection coefficient as 18 watts per meter degrees Kelvin. Next, specify the emissivity as 0.25. And click OK. After that, switch to the structural analysis case. Here, we will define structural restraints and loads. To do so, select Clamp from the Command section. Now select the bottom face of the build tray. And click OK. We will now edit the thermal and structural step definitions. Go to the Procedures section from the Action toolbar. And select Edit Current Step. Under the Static Step Definition dialog box, we cannot see the magnitude of the total step time, initial time increment, or maximum time increment. The reason is because they are computed by the powder bed fabrication app. So, in order to fill in the gaps, we need to update our simulation. For that, I will go to the Assistant panel, and click on the Update tool. When the update has completed, go back to the Edit Current Step option. We can now visualize the total step time, initial and maximum time increment. For additional control, we will edit the initial and maximum time increment. Set the initial time increment to 150 seconds. And the maximum time increment to 1000 seconds. Then, click OK. Similarly, we will edit the step time for the thermal analysis case. And specify the values. The pre-processing is now complete. And we can simulate the process. From the Assistant panel, click on Simulate. Here, make any necessary changes to the number of cores. I will use 4 cores for both the analysis cases. When the analysis has completed, we are going to visualize the results. To do so, click on Results from the Assistant panel. This is the temperature profile for the bridge geometry. You can use the Play Animation tab to animate the results over time. From the Plot dialog box, switch to the Structural Analysis case and select Displacement as a plot to visualize the displacement. Here, we can cycle through the frames to see the layer-by-layer build of the part and the corresponding displacement. This concludes our first video enablement manual session. I hope you found this material helpful, and hope you come back soon for more lessons. Thank you very much for watching, and have a nice day.